My name is Kamyab Cornett, and this is Lab 2 for Physics 2211. The purpose of this lab is to record an object's movement on a vertical plane and to create computational models to represent that movement, one with drag, the other without. The equation F equals ma is there to model the effect that gravity played into the movement of an object. Position and velocity update were used in the GlowScript code to model the movement of the ball. The drag equation shown was used in one of the two computational models so that the results from that computational model would more closely resemble the data observed from the object falling. The system is a paper ball that I dropped, and the surroundings are the air around it. The ball starts from a height of 147 centimeters and a velocity of 0. For the results, as expected, the model that incorporated drag was a more accurate model than the model that solely used mass and gravitational forces. This is the graph I created using Excel. I used a line graph because I thought it would best convey the results for this lab. According to Tracker, my ball took exactly 0.60 seconds to reach the ground from a height of 147 centimeters. These are the modifications I made to the skeleton code provided that led to me creating the model without drag. My paper ball started at 147 centimeters with a velocity of 0. The force acting upon the ball was equivalent to the ball's mass, 0.0045 kilograms, times g, negative 9.8. Then I plugged the updated FNet into the velocity update formula, and that allowed me to use the new velocities in the position update formula, thus creating a graph on the next slide. As you can see, the graph is moderately accurate, but since it doesn't account for drag, the ball is expected to reach the ground sooner than in reality. This is corrected in the next model. These edits were made along with the edits in the first code. I know it is rather inefficient the way I did it, but I created the constant for the drag equation in one variable with a b value of 0.0023 and separately created the unit vector for velocity. Then I created the force of the drag vector and placed it in the FNet equation so that it was opposite the force of gravity. The velocity and position update equation stayed the same. This is the updated graph with drag factored in. As you can see, the model that factors in drag is much more accurate than the one without. As for errors, we assume that the ball is only being influenced by gravity and drag, but other factors could have changed the results as well. The AC in the room could have very well changed the trajectory of an object with such low mass. The b value used for the drag equation could very well have been incorrect, and many other things that were not accounted for could easily have been cast aside. If the ball reaches a terminal velocity, this means that the force of drag is acting equally against the force of gravity. This means that the net force is 0, and thus the acceleration of the object is 0, thus the change in velocity is nothing. Changing the initial velocity would have no effect on the terminal velocity of the ball. The terminal velocity is only met when the force of drag is equal to the force of gravity. As we can see in the computational model, after a certain amount of time, no matter how fast the object, it begins to reach a point where the acceleration is 0.